Could we smell alien breath from 100 light-years away? Yes, by splitting starlight, we can read another world's air. The immediate takeaway is simple: the mix of gases holds the answer. Oxygen with methane means constant resupply because they destroy each other fast. Carbon dioxide with carbon monoxide suggests hot rocks, not biology. We already do this with telescopes that catch thin rainbows. The data look like barcodes where some colors dim slightly. Those dips are fingerprints for gases like water and ozone, so if someone is out there, their air can whisper back. A star dims softly as a small planet cuts across it. The planet's rim glows, thin as a halo at sunset. That glowing rim imprints its chemistry on the star's light. A biosignature is any detectable sign that living processes maintain. You care because this is a remote breath test for life. It lets us separate living worlds from dead rocks with confidence. Light passes through the rim, and specific colors get absorbed. Those colors match molecules because electrons jump between set energy levels. We record the spectrum, then subtract the star and instrument quirks. What remains is a forest of tiny dips across wavelengths. Software fits models, and out comes a gas mix with uncertainties. Rule of thumb: more lines means more trust in the answer. Example in real terms: JWST measured carbon dioxide on a hot world. The depth was around 50 parts per million in starlight. That is like noticing a fly cross a lighthouse beam. For cooler Earth-sized targets, the signals are smaller but steady. Water vapor might carve dips of a few parts per million. Oxygen leaves features near 1.0 micron and shorter wavelengths. Methane shows up near 3.3 microns in the infrared. If you see both at the same time, flags go up. Add disequilibrium math and you can score chemistry against geology. Scientists run scenarios like volcanoes plus sunlight and compare spectra. When no non-living recipe reproduces the mix, confidence climbs. Net result: reading atmospheres turns light into a biological probability. Now picture a desert planet with salty lakes under a red sun. Its air could hold oxygen, but not from forests or algae. Oxygen can build up when water splits under harsh ultraviolet light. A false positive is a life-like signal from non-living chemistry. It matters because chasing mirages wastes precious telescope time. Context saves you because planets are not blank slates in space. Start with the star, since red dwarfs blast frequent flares. Strong flares strip hydrogen, leaving oxygen behind as a residue. Then check mass, temperature, and whether oceans could persist for eons. Tidal locking changes winds and can trap ice on the dark side. Next, look for partner gases that stabilize or destabilize mixtures. Nitrogen and carbon dioxide buffer climates, while methane destabilizes oxygen. If oxygen appears alone, beware the easy photochemistry explanation. If oxygen joins methane and nitrous oxide, start leaning toward biology. Tiny test: ask if the planet can keep that mix stable. Without life, oxygen and methane cancel within tens of years. With life, both refill continuously from breath, waste, and microbes. The trick is timing, so you want repeat spectra across seasons. You also want day-side and night-side glimpses if possible. One famous estimate needs several transits per gas to be sure. That can mean dozens of hours on one dim star. Bottom line, the sky can trick you, unless you read the whole scene. There are more planets than grains of beach sand here. The galaxy holds hundreds of billions of suns and vast time, yet the sky stays quiet, which is the unsettling part. The Fermi paradox is that contrast between expectation and silence. You should care because silence itself is a clue to behavior. It shapes how loudly we search and how carefully we announce. One path says life is rare because starts are unlikely. Another says life is common, but intelligence seldom lasts long. A third says intelligence lasts but chooses to stay very quiet. The speed limit of light also shrinks reachable neighborhoods dramatically. Signals spread as spheres, and they fade with the square. To shout across 1,000 light-years takes absurd transmitter power. Example in real terms: a narrowband radio beacon can travel far. A 1 megawatt beacon with a big dish can beat noise. Our searches scan hertz-wide channels across gigahertz of spectrum. We also scan for repeating patterns that machines would produce. The Drake equation bundles these unknowns into rough multipliers. Some choices yield thousands of chatting cultures in the galaxy. Other choices return numbers below 1 for our whole sky. So the picture is sobering uncertainty, plus a very large stage. Rows of dishes listen to the quiet under a cold sky. Each dish tracks stars and feeds recordings into racks of servers. A search pipeline hunts for narrow tones that stand out from noise. A technosignature is any detectable trace of technology, not biology. This matters because machines can outshine microbes across interstellar space. A city is dim, but a beacon can be blazing clear. The pipeline works like a layered filter with sanity checks. First, signals are split by frequency and inspected for spikes. Then algorithms flag spikes that drift smoothly with Earth's rotation. That drift is key because it separates sky from our gadgets. Next, telescopes nod away to see if the spike follows. Real sky signals stay put on the star, while junk stays local. Then a second observatory repeats the scan, hours or days later. If it repeats, the odds tilt away from random static. Lasers get a similar treatment, with cameras catching nanosecond flashes. Instruments compare frames and hunt for same pixel, same timing. Example, the Breakthrough Listen program scans billions of channels continuously. It covers 1 to 10 gigahertz and looks for narrow hertz. It has excluded many false alarms, including satellites and aircraft. The WOW signal remains intriguing, but never repeated in decades. Common mistake is thinking one blip proves contact overnight. Verification is brutal and designed to break weak claims. Bottom line, any shout would survive independent teams chewing the data. Bright radio beacons are not the only unnatural glow out there. Technology leaks heat, light, and chemicals into its environment over time. That mess can be visible from far away with patience. A waste heat search looks for extra mid-infrared from a system. If a civilization builds giant collectors, they must re-radiate absorbed energy. That re-radiation glows like warm dust, but with a smoother color. A Dyson sphere is the extreme case, a star wrapped fully. The realistic case is partial structures, like swarms or belts of collectors. You care because heat obeys physics and cannot hide perfectly. It scales with power use, which tracks development and population growth. Observatories survey thousands of stars for odd mid-infrared colors. They compare to dust models and tag the strange outliers carefully. Another avenue checks for industrial molecules, like chlorofluorocarbons high aloft. Those leave sharp features near 8 to 12 microns in spectra. Nature barely makes them, so any detection sticks out like neon. Night-side imaging tempts people because cities shine where it is dark. In practice, night-side glows are tiny and stars are blindingly bright. You would need enormous space telescopes with clean starlight suppression, star shades. Example, a partial Dyson swarm might radiate at 300 Kelvin. That peak sits near 10 microns and outshines cold dust nearby. A 1% enclosure could radiate about 10 to the power of 15 watts. Telescopes like JWST can already see that glow for close targets. Net result, waste heat and chemicals widen the net beyond radio. A jet of ice sprays from a crack in the dark. That plume is a gift because it carries ocean secrets upward. Moons like Enceladus and Europa hide saltwater under thick ice. An ocean world is a small body with liquid water inside. It matters because samples reach space naturally, where we can grab them. No drilling is needed, only careful flying through the rising spray. Instruments sniff molecules, weigh grains, and count complex organics by mass. They also check salts in tiny bubbles of trapped gases. The pattern reveals sources like hydrothermal vents in warm rocks. On Earth, vent chemistry feeds microbes without sunlight at all. The same gradients could feed life in sealed alien oceans. Example in real terms, Cassini flew through Enceladus more than a dozen times. It found tiny silica grains, pointing to hot rock and water contact. It saw hydrogen, which vents often release during serpentinization reactions. Future probes can add life-friendly tests, like chiral preferences in molecules. They can also check amino acid families and carbon isotope ratios. Tiny tests ask if complex molecules show a handedness bias. Biology picks one hand, while chemistry without cells splits evenly. Another test asks if sizes cluster like polymer chains from enzymes. Put several tests together, and statistical confidence starts to build. Bottom line, nearby oceans offer doable searches within our lifetimes. A narrow tone appears at 2 in the morning, then steadies. The room goes silent, while the screen fills with a clean spike. People trade glances, then start the boring work that matters. A candidate is a signal that passes the first quick filters. You should care because the next hours decide history or noise. The process prevents excitement from outrunning the evidence on the table. First, call another observatory, preferably far away, under different radio skies. Share sky coordinates, frequency, and the exact drift rate per second. Ask them to point, record, and check on off and on cycles. If both sites see the same drift, that is a good sign. Next, change receivers and rule out harmonics from local electronics nearby. Switch polarizations and confirm the signal behaves like a sky source. Then wait a day and schedule another pass on that star. A true beacon would repeat because transmitters run long campaigns. A passing satellite will not, and aircraft will be long gone. If it repeats, you publish coordinates and data immediately and broadly. Multiple teams pile on and try creative ways to falsify it. Example, Breakthrough Listen once flagged repeating candidates from our own network gear. Those died quickly because the drift pattern failed a simple test. The net result is a culture of proof, not romance. The quiet sky is not empty, it is data and waiting. Every non-detection tightens limits and teaches our instruments new tricks. Every spectrum on an exoplanet turns faint rainbows into chemistry. If we do find a real mix, we will know why. It will be oxygen with a partner and a stable story. It will be a breath we can read from very far away. The first contact could be a graph, not a saucer over clouds. That is fine because clarity beats drama when you change history. I like that patience, and I like that we can practice. We can listen better, model smarter, and share fast across teams. If this kind of grounded hunt is your thing, stick around. I make deep dives that keep the wonder and skip the fluff. Next week we chase a nearby ocean plume with open eyes.